we said that probability is closely related to counting. So now let's see some properties of probability that very much come from the counting that we've done. So first of all, let's talk about complementary events. So let's say we have an event in some sample space. What is the probability of the complementary event, which is E complement? And by this, we mean the complement inside S. So you could rewrite this as S without E. And this should remind us of a strategy that we talked about in counting, which I think I called work from either end. So if you remember that, then you can probably predict what is going to happen here, and you will be very bored while you listen to me explain it all over again. So, well, yeah, let me say what this meant for counting was that if you want to count the number of objects of some type inside a bigger set, then you can either count them directly, or you can count the complement and then subtract that from the total. So this is going to work exactly the same way. So the probability of E complement, by our definition, is the cardinality of E complement divided by the cardinality of S. And the cardinality of E complement is equal to the cardinality of S minus the cardinality of E. So that is essentially the counting rule that I'm referring to. And this, of course, you can split up into S over S and then E over S. I shouldn't do the slash because I'm not canceling them, but S over S minus E over S. So what you get is 1 minus cardinality of E over cardinality of S, because that is 1, of course. And by our definition, this is just 1 minus the probability of E. So just to write that again, the probability of the complement of E is 1 minus the probability of E. So the probability of the complement is just the probability of the original thing subtracted from the total. The total probability is 1. Let's do an example of this. So let's say we flip a coin 10 times. We think it is a fair coin, so the probability of heads is 1/2, and of tails is also 1/2. What's the probability? Let me just write it like this. What's the probability that in 10 flips, we get at least 1 heads? So the point is that in this case, E is complicated. It could be 1 heads, or 2 heads, or more in different orders, etc., etc. But E complement is simple. In fact, it is a single outcome. The complement of getting at least 1 head is getting exactly 0 heads. And there is only one way to do that, which is tails, tails, bunch of tails. And let's quickly say S is our sample space. We can think of as strings of 10 letters H or T. So cardinality of S is, how many ways can we write down a string of 10 H's and T's? Here's another little counting problem. And we've seen some examples like this. Basically, we have 10 slots. We can use a straightforward product rule, right? We have 10 slots, and each one can take 2 options. So that is just 2 to the 10. So the probability of E is 1 minus the probability of E complement, which is 1 minus 1 is the cardinality of E complement, because it's a single outcome, this one. And the cardinality of S is 2 to the 10. So that is our probability. And if we want to, we can rewrite this. So 2 to the 10th is 1024. So 1 minus 1 over 2 to the 10th is 1023 over 1024. And this is about 0.999. So you flip a coin 10 times, you are very confident that you will get at least 1 head. In fact, you might say that you are about 99.9% confident. Quantify it, since you are doing probability. So our next thing is unions of events. And for this, the counting rule that we should remember is how to count a union of 2 sets, which is the inclusion-exclusion rule. So the probability of event E1 union event E2. So this you can think of saying, what is the probability that event 1 happens or event 2 happens? That essentially corresponds to taking the union. So this is equal to cardinality of E1 union E2 over cardinality of S. And we just apply inclusion-exclusion to this top part. And what we get is, remember inclusion-exclusion, what does it say? It says that the cardinality of the union is the cardinality of first plus the cardinality of the second minus the cardinality of the intersection. So we can rewrite that just by separating out the fraction. And this now, we recognize these as probabilities of E1, E2, and the intersection. So what we have shown, just to write it again, is the probability of the union is the probability of the first plus the probability of the second minus the probability of both. So let's just do a quick example of this. What is the probability that a randomly chosen card from a deck is a spade or an ace. So this is precisely the kind of situation where we have this or that we can turn into a union of two events. So let's call E1 being a spade, then let's call E2 being an ace, and then E1 intersects E2 means that you are the ace of spades. So the probability of E1, let's not write it out in full, let's just do it in our heads. How many spades are there in a deck of cards? There are 13 cards of each suit, so there's 13 spades, divided by 52. 52 is the total number of cards. How many aces are there in a deck of cards? There are 4 out of 52 cards total. And how many ace of spades are there in a deck of cards? There is only 1. So the probability that we get a spade or an ace is 1352 plus 4 over 52 minus 1 over 52, which is, what is this? I believe this is 16 over 52, which is 4/13. And it's about 0.31. So this is how you find the probability of a union of two events. We can get a little bit more general than that. In general, if EI are a collection of disjoint events, meaning disjoint in the sense of subsets of our sample space, then they add in a very simple way. The probability of the union is just the sum of the probabilities. So this, of course, is coming from the fact that they are disjoint. So the intersection term in this kind of rule disappears. The intersection is empty, so the probability of getting the intersection is 0. But you know, generally, if you have a bunch of events, they will not necessarily be disjoint. So if they're not disjoint, then we can't say this anymore. We will no longer have this exact formula until we talk about inclusion-exclusion in a week or so. But for now, we can still say that the probability of the union is at most the sum of the probabilities. So if they're disjoint, these two things are equal. If they're not disjoint, this is still the biggest that the probability of the union can be.